Okay, Organic Chemistry 1. Let's move on and talk about molecular geometry a little bit. And in order for you to understand molecular geometry, you have to be pretty solid on your VSEPR theory, which is valence shell electron pair repulsion theory, which is nothing more than electrons want to be free. You know, they want to have as much space as they can. Don't fence me in, right? Is kind of the motto of an electron. So when we have pairs of electrons, whether they're in bonds or lone pairs, or if we have double bonds or triple bonds or unpaired electrons, they always want to get as far from each other as possible, right? They seek to repel each other. And so in order for us to um, determine molecular geometry, we have to start with a steric number. And so a steric number is related to the number of sigma bonds and the number of lone pairs. So we'll put here steric number, it's number of sigma bonds and number of lone pairs. So if we look at all three of these molecules, here we have methane at the beginning, and then we have ammonia, NH3, and then we have water, of course, down here. They all have the same steric number. They all have a steric number of 4. Why? Because methane has 1, 2, 3, 4 sigma bonds. It's got no lone pairs on the carbon, but it's got 4 sigma bonds, and so its steric number is 4. If we look at ammonia, it's got 1, 2, 3 sigma bonds and 1 lone pair. Therefore, it has a steric number of 4. And water has 2 sigma bonds and 2 lone pairs. And so its steric number is also 4. So again, all 3 of these molecules, the central atom has a steric number of 4. And so how are those electrons going to seek to repel each other? They're going to get as far away from each other as possible. And the electron geometry for all 3 of these molecules will be the same. It will be tetrahedral. However, their molecular geometry will not be the same, will it? So steric number relates directly to the hybridization of the central atom. If the steric number is 4, your central atom has sp3 hybridization. If it's 3, it's sp2 hybridized. And if your steric number is 2, it is sp hybridized. So that means that all 3 of these atoms, the carbon, the nitrogen, and the oxygen, all of them are sp3. All are sp3 hybridized, right? Because the steric number is 4 for each one of them. Now, again, I told you you need to know the difference between electron geometry and molecular geometry. It says here for an sp3 hybridized atom, the 4 valence electron pairs, whether it's a bond or a lone pair, they're going to form a tetrahedral electron group geometry, right? Methane has 4 sigma bonds, 1, 2, 3, 4. So they spread out as far as possible. And it's electron geometry, or it's electron group geometry, which is the same thing as me saying electron geometry. Geometry considers bonds and lone pairs. So since the carbon has 4 bonds and no lone pairs, its electron geometry is tetrahedral. In ammonia, the nitrogen has 3 sigma bonds and 1 lone pair, steric number of 4. So its electron geometry is tetrahedral. And the water molecule also has an electron geometry, which is tetrahedral. Now, if you look at the bond angles in methane, everything is exactly 109.5 degrees. But if you look at the ammonia molecule, you'll see that the bond angles are a little less. Why is that? It's because of the lone pair on the nitrogen, which pushes down on those nitrogen-hydrogen bonds, brings them a little closer together. Same thing happens in water. We have 2 lone pairs, which pushes the 2 oxygen-hydrogen bonds even closer together and tightens that bond angle to 105 degrees. It's around 104.7, I think, but who's counting, okay? All you need to know is that the more electron lone pairs that you have, they push the bonds down and the bond angles get a little bit smaller with every lone pair. Now, again, I told you that electron geometry and molecular geometry are 2 different things. So if you look at these 3 molecules, methane, ammonia, and water, this is the electron geometry. You see that they're all identical, but their molecular geometries are different, aren't they? because electron geometry considers bonds and lone pairs, whereas molecular geometry considers bonds only. Okay, so if I look at the bonds surrounding the carbon on the methane molecule, I have 4 bonds, so it's also tetrahedral. But when I look at the ammonia molecule, I've only got these 3 bonds to the nitrogen, and therefore it's trigonal pyramidal. If I look at water, even though my electron geometry is tetrahedral, my molecular geometry is bent, right? Because I have the bent shape, the bent molecular geometry. Is steric number the same thing as red? Not exactly, because a region of electron density, or a red, RED, refers to, it can be a single bond, it can be a double bond, it can be a triple bond, it could be a lone pair, and it can be an unpaired electron. Whereas the steric number, we're only talking about sigma bonds and lone pairs. So if you look at molecules like boron trifluoride or beryllium hydride, these molecules down here, you need to know the difference between molecular geometry and electron geometry. You can see that they're the same in both of these cases, but you need to understand the why in organic chemistry. So this is a table that comes straight out of our textbook. It's a summary of molecular geometry. If you have a steric number of 4, your electron geometry, so that's what's here, this is electron geometry, is going to be the same for all of them. Everything will be tetrahedral. But if you have 1 lone pair in the central atom, it's trigonal pyramidal. If you have 2 lone pairs in the central atom, your molecular geometry is bent. So these are molecular geometries down here. Geometry. Okay, if you have a steric number of 3, you have a trigonal planar electron geometry no matter what. But if you have 1 lone pair, you have a bent geometry, and if you have no lone pairs, it's trigonal planar. If you have sp hybridization, your electron geometry is going to be linear, and you'll have no lone, or when you have no lone pairs, or you won't have any lone pairs, sorry, it's just going to be linear all the time. All right, there we go. So that's a summary. Some examples, if we just pencil in a couple examples here. So methane would be a good example of tetrahedral. Trigonal pyramidal, the example we looked at was ammonia for bent. Water, boron trifluoride is a good example for trigonal planar. And then beryllium hydride, BeH2, is a good example of linear. Excuse me. Well, with that in mind, let's try a practice problem. The best way to master any content in a chemistry class is to practice what you've learned. So could anybody predict the molecular geometry? This is called a borohydride. It's a polyatomic ion. But could anybody predict what the molecular geometry of borohydride would be? BH4. And it's not a trick. Yeah, it's going to be tetrahedral. How do we figure that out? Because the steric number, okay, the steric number for my boron, it's got 4 sigma bonds. Okay, it's got 0 lone pairs. So my steric number is 4 plus 0 is 4. Therefore, my molecular geometry, or sorry, my electron geometry will be tetrahedral. But since I've got 0 lone pairs, my molecular geometry is also going to be tetrahedral. If you're wondering, how did you figure that out? Look, go back to the table. If you've got a steric number of 4, your electron geometry is tetrahedral. If you have no lone pairs, your molecular geometry is tetrahedral. So if we wanted to draw the molecular geometry out properly for the borohydride, we put the boron, we'll put 2 hydrogens in the plane of the page or the screen, and then we'll put one of the hydrogens going back like this, another one coming out like this, put the formal charge on our boron. Our bond angles would be around 109.5 degrees. All right, next we have boron trifluoride. Okay, if we look at the boron, and we want to calculate the steric number, it's got 3 sigma bonds. It's got 0 lone pairs. We tally that up. We have a steric number of 3. So that means its electron geometry, it's going to be equal to, or it's going to be trigonal planar. Okay. Again, it's got 0 lone pairs, so its molecular geometry will also be trigonal planar. So there's nothing wrong with the way that it's drawn there, except they've left out the lone pairs on the fluorines. So we could put those in. We have our boron with the 3 fluorines. We'll put in all the lone pairs like that. And then we'll put in the bond angle, which is 120 degrees. And so this is trigonal planar. There you go. We've used VSEPR theory to predict the molecular geometry and the electron geometry for both of these structures. Well, not only do you have to understand Lewis structures, VSEPR theory in order to draw molecular geometries properly, but you have to understand molecular polarity and dipoles. Remember we talked about polar bonds earlier on today. We talked about what a dipole moment is. Let's say you have a bond between carbon and oxygen, and we said you're going to have a dipole going in this direction, right? Because it's a polar bond. The difference in electronegativity between carbon and oxygen, delta En is equal to 1.0, so it's a polar covalent bond, right? We said you could also represent the polar covalent bond. You could put a delta minus by the oxygen, a delta plus by the carbon to represent that they're partially negative and partially positive, respectively. Dipole moments are measured in units called dBs. I'm never going to ask you to calculate any kind of or do any math with respect to dipole moments at all. But let me just show you quickly where the dipole moment comes from. Or did I leave that out? No, okay. I was going to tell you a little bit about where it comes from, but I'll just say I'll never ask you to do any calculations in dBi. Okay, so don't worry about that. Let's just move on to things that I will ask you about. So let's talk about molecular polarity. Now, again, this is another example of where a model kit might come in handy. So let's say you have a molecule like this one right here, okay? This is called dichloromethane. So dichloromethane. Okay, in dichloromethane, you can see that there are 2 polar bonds, aren't there? Right, there's a dipole going between the carbon and the chlorine. Now, that one, the carbon and the chlorine, is not a huge difference in electronegativity. It's 0.5, but hey, it's enough that we could say this is partially negative, this is partially negative, right? This is partially positive. But we'll just leave the vectors there for now. Now, if I have 2 vectors pointing like this, and another one pointing like this, what if I add those 2 vectors together, right? Now, I'm not an expert at doing this kind of thing, right? But if you were to add those 2 vectors together like this, what's the resultant vector? Is that you're going to have, you're going to have a vector going off in this direction like this. So the net dipole is going to be going in that direction, right? The molecular dipole moment is going to be pointing off in this direction like this. So what does that mean? That means that this is a polar molecule. Polar molecule. Okay, and you've got to be able to add those vectors in your mind a little bit. Okay, you've got to be able to add vectors together. So let's say you have a molecule like ammonia, right? You have the dipoles going from the hydrogen towards the nitrogen, right? Because nitrogen has an electronegativity of 3.0. Hydrogen has an electronegativity of 2.1. So we have those 3 dipoles, and you can also draw a dipole on the lone pair, right? Going towards the lone pair. So if you add up all 4 of these, the resultant dipole is going to be going straight up like this. So we have a net dipole moment. So that tells you that ammonia is also a polar molecule. If you look at water, if you add up all the dipoles from the 2 hydrogen-oxygen bonds and the dipoles to the lone pairs, you can see that water is also a polar molecule, right? It has a net dipole moment if you tally up those vectors. And so again, when you have multiple polar bonds, the sum is going to equal the overall dipole moment for the molecule. Give me a thumbs up if you follow me on that concept. You have to add the vectors together. Anybody with me on that? Okay, thanks, Bruna. Good. Great. So you've got to be able to determine when a molecule is polar and when it is not polar. Well, in order for you to understand or be able to determine if a molecule is polar or not, you've got to know the molecule's geometry way before you can do anything else, right? You've got to be able to draw the proper molecular geometry. If it's not drawn properly, you won't be able to assess the polarity nearly as well, okay? It'll be very difficult to do that. All right, it says here, would water have a different dipole moment if it was linear instead of bent, right? You can clearly see that water is a bent molecule. If water was linear, let's say you drew water like this, okay? And you said, hey, water's a linear molecule, which is not true. But then you'd have a dipole going in this direction and a dipole going in that direction, and they would cancel each other out. Same thing with the lone pairs. You'd have one going in this direction, one going that direction, and all dipoles would cancel. Okay, and then you'd have a nonpolar molecule. So it would give you the wrong answer. And so that's why, you know, even people who don't know anything about chemistry will oftentimes draw water, you know, they'll draw it bent like this because the fact that water is bent is what imparts the polarity to the molecule. And it's very important that water is a polar molecule. Otherwise, we would cease to exist. All right, so molecular polarity in dipoles. Something that you'll see throughout our textbook are EPMs, or electrostatic potential maps, which we use to give a visual depiction of polarity. Organic chemists will very rarely use electrostatic potential maps when they're talking to each other, but in a textbook for students who are just learning the subject, I think they're really great. In our textbook, whenever you see a rainbow colored electrostatic potential map like this one here for chloromethane, the more red that you see means there's more electron density, and the more blue color you have means less electron density. So they can be really handy when we're looking at reactivity of molecules later on. Electrostatic potential maps will come up quite a bit. Now, in terms of molecular polarity and dipoles, I told you I would never ask you to calculate a dipole moment. I think there might even be a couple questions in our textbook about calculating dipole moments. We'll not ask you how to calculate with a calculator a dipole moment, but you should know what the unit of polarity is, and that's the debye. And at the higher the number, so you have, let's say, 2.69 debye for acetone, and you have 0 debye for carbon tetrachloride, the higher the dipole moment, the more polar the molecule, okay? So you can see that polarity is increasing as we go from ethanol to methanol to water to chloromethane, all the way up to acetone, like that. So that's really all you have to know about that. Again, no calculations will be asked. So with that in mind, it says identify whether each of the following compounds exhibits a molecular dipole moment. For compounds that do, indicate the direction of the net molecular dipole moment. You know what? I think it might actually be easier to start with the last one, which is J, the one on the very bottom here. If I redraw that molecule, or maybe we'll just zoom in on it like this. Are there any polar bonds in this molecule in J? So this would be trans 1, 2, or it'd be trans dichloroethylene. Are there any polar bonds in this molecule? J, the J molecule? Yeah, thanks, Warren. Yeah, there absolutely are. Right? The carbon-carbon bond is not a polar bond. The carbon-hydrogen bonds, those aren't polar either. But there are two polar bonds, aren't there? Right? The bond between the carbon and the chlorine going like this, and the bond between this carbon and this chlorine, we have a vector going like that. Okay? So I've got a vector going like this off in this direction, and I've got another vector going down in this direction, like that. What's going to happen if I try to add those two vectors together? What are they going to do? They're going to cancel each other out, right? So dipoles cancel. Therefore, non-polar. There you go. So they cancel each other out. So this is a nonpolar molecule. There we go. Let's take a look at this one here. This is dimethyl ether. If you remember at the very beginning of the lecture today, when we were talking about constitutional isomers, this molecule did come up, and I actually showed you the connectivity of the molecule. So let's draw. We have, oops, carbon, oxygen, carbon, like this. Could anybody take a guess, or just does anybody have any inclination as to whether this is a polar molecule or not? The way it's drawn, it looks like it's nonpolar, doesn't it? Right? You know that all of these bonds, right? This bond, this bond, this bond, these are, right? These are all, let me use my red pen, nonpolar bonds, aren't they? Okay. Are there any polar bonds in the molecule? Absolutely. Right? This carbon-oxygen bond and this carbon-oxygen bond, these are polar bonds. Okay? Now, it's supposed to be bent at the oxygen, isn't it, Kelly? Absolutely. Right? Because the steric number of that oxygen is 4. It has a steric number of 4. And so if we were to draw that oxygen and show the molecular geometry, we have one CH3 up here. There's nothing polar in that, so I'm just going to draw it condensed. I have another CH3 down here. I have one lone pair going in the back, and I have one lone pair coming up in the front like this. Let's draw all the dipoles. I've got a dipole going this way. I've got a dipole going this way, and then I have 2 dipoles going this way. If you tally up all 4 of those dipoles, your resultant dipole is going to be going off in this direction. And so dimethyl ether is a polar molecule. So net dipole, therefore, polar. In the interest of time, I'm going to skip D. Again, you have the solution to that one in the solutions manual. So I'm going to get you to take a look at that one on your own time. And if we have time later on, maybe we'll come back and take a look at it. Well, let's switch gears for a second and talk about intermolecular forces. I know that some of you have never had me as an instructor before, but before I became a chemistry teacher, I worked as a research scientist in the pharmaceutical industry for about 15 years. And, you know, whenever I talk to friends of mine that were former colleagues in the pharmaceutical industry, I'll tell them, now that I'm a chemistry teacher, I feel like my life could be summarized like this. I wake up in the morning, I brush my teeth, and then I talk about intermolecular forces until I go to bed. Because intermolecular forces come up in virtually all chemistry classes. So whether I'm teaching this class, general chemistry, analytical chemistry, biochemistry, it doesn't matter. Intermolecular forces always come up. So I shorten this to IMFs, intermolecular forces. And if you studied intermolecular forces in general chemistry, and you all should have, you would have learned other intermolecular forces besides the 3 that are listed here. Like you would have learned ion dipole and ion induced dipole and different things like that, which we're not going to worry about. But the reason intermolecular forces are so important is because properties, physical properties like solubility, boiling points, melting points, densities, refractive indices, which is something that you probably haven't learned yet, but all of these things are a result of the forces of attraction between molecules. And so neutral molecules, whether they're polar or nonpolar, are going to be attracted to each other some way. And the 3 types of intermolecular forces that you need to understand are dipole-dipole interactions, hydrogen bonding, and dispersion forces, which we sometimes refer to as London forces or fleeting dipole forces. Now, these are not listed here in any particular order because dispersion forces are the weakest of these 3, and hydrogen bonding are the strongest of these 3 types of intermolecular forces. So again, you've got to really know what intermolecular forces are, because later on we're going to talk about boiling points and melting points of molecules. Okay, and you want to understand why molecules have certain physical properties. It's also important if you're taking the lab class, and I know that several of you are enrolled in Chemistry 3102 at the moment. All right. Now, if you're wondering what the heck are intermolecular forces, well, the forces that hold, let's say you have a water molecule. Okay, the actual bonds that hold the water molecule together, these are intramolecular forces. Okay, actual bonds. Okay, we'll just call it bonds. Okay, those are intramolecular forces, right? If you think of intranational, it's like inside the same country. But let's say you have a glass of water. Okay, you have a glass of water like this. And then there's some kind of force that's preventing those molecules from just evaporating, poof, you know, immediately into the air. If anybody here has ever spilled gasoline before, if you've ever had filled up your lawnmower and spilled gasoline, it doesn't take very long for gasoline to evaporate, does it? Right? Whereas if you spill water, it takes a long time for it to evaporate. It does evaporate eventually, but it takes a lot longer. Why? Because the intermolecular forces that hold the individual water molecules together are much stronger than the intermolecular forces that hold those molecules that make up the mixture called gasoline together. So we need to understand what those intermolecular forces are. Let's say you have a dipole in a molecule. Earlier on, we talked about the molecule acetone, which is this molecule here. So we have a double bond between carbon and oxygen. And we know that that's the only polar bond in the entire molecule, right? We have a dipole going this way. So if we have a bunch of molecules of acetone in a liquid, you know, or in the liquid phase, right? Because acetone is a liquid at room temperature. Well, are they just going to align themselves randomly? To some extent, probably yes. But what about the permanent dipole in the molecule, right? If I have a molecule of acetone, like this one right here, okay? And if the oxygen is partially negative and the carbon is partially positive, what's going to happen is that acetone molecule is just going to be floating around in the liquid, okay? But it's going to align itself in such a way that it's going to try to maximize the electrostatic interaction between the delta negative, I was trying to highlight that, the delta negative on another oxygen with the delta plus on another carbon, right? Let's say we have another molecule of acetone, copy, paste, right? And it's just floating around like this. This one might align itself over here to maximize the attractive force between the delta minus of the oxygen and another delta plus on another carbon like that. So basically, what happens is we have permanent dipoles in a polar molecule, and so the dipoles will arrange themselves so that the opposite charges maximize their attractive forces. And that's what a dipole-dipole force is. Now it says molecules with the, while similar molecules without dipole-dipole interactions, such as isobutylene, have lower boiling and melting points. Let me show you what I mean by that. So here we have acetone, and I showed you why that's a polar molecule. But if you have isobutylene, to the untrained eye, to somebody who hasn't studied chemistry before, they might think, man, this molecule looks almost the exact same. We got a couple of single bonds, I got a double bond. Oh yeah, it's the same. Well, in isobutylene, there are no polar bonds, and so there's no dipole in isobutylene, right? So there's no dipole-dipole forces that are going to be experienced between two molecules or more of isobutylene, and therefore its boiling point and melting point is much lower than the boiling point and melting point of acetone. Why? Because the only type of intermolecular force that isobutylene can experience are London forces, and I'll talk about what those are in a bit. London forces only, okay? Whereas acetone does experience London forces, but it also experiences dipole-dipole forces. So dipole, 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 okay? And I'll just leave that there because a dipole-dipole force is stronger than a London force. All right. Give me a thumbs up if you follow me on the concept of a dipole-dipole force. Cha? No? Okay, cool. Good. It's a really important, concept, but you think about it. I told you that this class was additive, right? You have to build up on the concepts. But think about it. In order to get this far, to understand that acetone is a polar molecule, and two molecules of acetone are going to have dipole-dipole forces. Think about all the things you have to understand. You have to understand bonding. You have to understand polarity. You have to understand electronegativity. You have to understand molecular geometry. You have to understand electrostatic forces, right? So you have to put all of those concepts together in order to understand dipole-dipole forces. All right, well, let's move on to from there and talk about hydrogen bonding, because if you understood what dipole-dipole forces are, my friend, you are going to understand what hydrogen bonding is. Because hydrogen bond is nothing more than a dipole-dipole force, but it's just a very strong dipole-dipole force. That's all it is, okay? So it's just a strong dipole-dipole attraction. Hydrogen bonds are strong because the partial positive and the partial negative charges are really, really powerful. That's all it is. Now, another thing that students will sometimes find a little annoying is that hydrogen bonding is not bonding. It's an intermolecular force. Look, I didn't invent it, okay? I didn't come up with anything bonding. It's just a type of intermolecular force, but we call it bonding because it's so much stronger than a dipole-dipole force, I guess. Anyhow, the hydrogen bond is the attractive force between a hydrogen that is bound to either, and you got to memorize this, a nitrogen, an oxygen, or a fluorine, and the lone pair on another electronegative atom. So let's say you have two water molecules. You have the delta minus on the oxygen. You have the delta plus on the hydrogen. You have the delta minus on the other oxygen, right? You have a delta plus over here. Well, you draw the hydrogen bond as the interaction between the delta plus on the hydrogen and a lone pair on another electronegative element, okay, the one with the delta minus. Let's say you have two molecules of ammonia, same type of deal, right? You have the delta minus here, delta minus here, delta plus here. I guess they already have the delta minus there. Anyhow, but you just draw a dashed line between the lone pair and the delta plus hydrogen like that. And that's how you represent hydrogen bonding. Let's say you had two molecules of HF. So HF, right? This shows fluorine. All right, how would I show it? If I was a student, I'd put delta plus here, delta minus here, and then I'd show the hydrogen bond like that, okay? Only when a hydrogen shares electrons with an oxygen, nitrogen, or fluorine, it's going to have a high enough partial positive charge that it can form a hydrogen bond. So here's two molecules of ethanol. So this is an ethanol molecule here, and here's another ethanol, and you can see the hydrogen bond there. A hydrogen bond is still 20 times weaker than a covalent bond, but again, it's much stronger than a dipole-dipole force. All right, there we go. Solvents that engage, and solvents, you guys know the difference between a solvent and a solute, right? Solute is the substance that's present in a smaller amount in a solution, and the solvent is the substance that's present in a larger amount. Well, a solvent that can engage in hydrogen bonding in organic chemistry, and there are lots of them, we call those protic solvents. So say, for example, you did a reaction in organic chemistry and your solvent was acetic acid. Since you have an oxygen-hydrogen bond, we call it a protic solvent, okay? Because it has the capability of hydrogen bonding. Whereas if you had other solvents like dimethyl sulfoxide or DMSO or diethyl ether or dimethyl ether, since those do not have oxygen-hydrogen bonds, they're not capable of hydrogen bonding, and so we call them aprotic solvents. So protic and aprotic solvents. Here's another example of hydrogen bonding in nitrogen-containing molecules. Hydrogen bonding helps us understand why these three molecules have very different boiling points, don't they? Right? You have trimethylamine, which has a boiling point of 3.5 degrees Celsius. Then you go up to ethylamine, right? It has the same molecular formula. All of these molecules are C3H9N, but since it has the capability of hydrogen bonding, it's got a higher boiling point. Then you go up to propylamine, which has the capability of twice as much hydrogen bonding. It has an even higher boiling point. Hydrogen bonding is responsible for the double helix in DNA. It's also responsible for the alpha helix in proteins. If you've ever studied the alpha helix in the beta pleated sheet, which is a type of secondary structure in proteins. Okay, so let's cover the last type of intermolecular force, and then I think we're going to call it a day because my voice is getting a little sore. And